To get the buildings to have a roof, we are going to go to building.js and let's get access to the base midpoints. So just the segment in the middle of the base there. We can do that by typing this and now averaging this base points of 0 with this base points of 1. And the second is going to be this base points of 2 and this base points of 3. And for these, we can also calculate the top versions on the top of the house. They are going to be the middle of the roof. So top midpoints are going to be base midpoints, but we have to offset them. And I'm just going to copy here this formula that we figured out previously. And we also need to think that if the roof is going to be on top, so these midpoints of the roof are going to be very high up, that's going to be the height of the building. So here, these are actually the height of the walls. And I'm going to use a smaller version of this height coefficient. So I will multiply it by 0.6. It's 60% of whatever this is. But here, base midpoints, I'm going to map them like this all the way to the top. And now we can use these top midpoints and also the ceiling points to get the roof parts. We will have 2 parts of the roof. And this is quite similar logic that we did for the sides. So roof polys, a new poly like this with ceiling points of 0, ceiling points of 3, top midpoints of 1, top midpoints of 0, and then another polygon, ceiling points of 2, ceiling points of 1, top midpoints of 0, top midpoints of 1. And now let's draw these polys. And we're going to do that here at the end after drawing the ceiling. So looping through the roof polys, asking them to draw themselves on the context. And here I'm going to make a little bit red color and a darker version for the stroke. Save and refresh. And this is what we get. I would like this middle line here, the strokes, to be a little bit thicker. So let's add here a line width of 8. Save, refresh. And now you can see these sides extending like this a little bit. It gives that kind of feeling. I'm not sure what this is called in English, but in Romanian it's strașină. So this strașină is here. And this looks a little bit not so nice here. We can use round line join instead to get a better shape. So I'm going to put here join round, and we need to implement this in the polygon primitive. So here let's add also join. By default it's going to be this meter, and here line join, set it to whatever join is. It's a little bit more expensive to calculate these round joins from processor point of view, so good to use them sparingly. Save and refresh. And now we don't get that strange effect there. One thing that does happen is here you can see one roof poly, the one at the back, is actually drawn on top of this one in the front. So we have to do the sorting here as well. I'm just going to go to building.js and copy here the sort we did to the sides. And after we have the roof polys, I will just paste it here, but with roof polys instead. Save and refresh. And now this doesn't happen anymore, no more problem there. One thing that I don't particularly like is this line here coming from the ceiling. We could set the stroke of the ceiling to white as well, not just a fill. Save and refresh. And it's better, but you can still see it a little bit from the side. Side wall also has this gray contour. Maybe if we make it white, but also a little bit thicker, it's going to cover it. And I'm going to go here and say line width of 6, save, refresh. Yeah, there's no problem here anymore. And one thing is this base that we are drawing here first, and it's covered by everything, so we don't really need it. Or we could change it a little bit so that the stroke here is going to be a transparent black stroke, and then we also give it a thicker width, maybe 20, like this. And if we do that and refresh, you can see a kind of a shadow around the house. I think that looks nice. And you can go on with this if you want to style things even more. I have a version where I drew door and window on the roadside of the house. I think it's nice, but the tutorial would just go on forever if I style these even more. And at some point, you're better off just using some 3D renderer and getting models from somewhere if you're gonna spend time to make such detailed things. But one thing I still want to do is mention this 3D effect. So it does make these very funny shapes here, becoming much more tall than the width. And these houses are meant to be opposite, like longer than they are. They are tall. And this looks a little bit funny, especially when you zoom out like this. So let's implement a better way of doing this. I'm going to start with the trees, actually, because they are simpler. And what I mean by better way is the tree will have an actual height, so 200 pixels. That's the height that you would see if the tree is really far away and you look at it from the side. And here, instead of height coefficient, just working with the heights instead. And what we have here is the difference between the viewpoint and the center, but we will also need to use the distance between the viewpoint and the center. So I'm going to copy this here before this top. And distance is going to be distance between this center and viewpoint. And this distance is going to tell us how much it should be offset, but it's not going to contribute directly to the offset. What we would like to have is a function between 0 and 1 that tells us how much to contribute relative to this height of the object. So when it's 1, when the object is far away, we basically look at it from the side. And that's when it's going to contribute the most, this height. And when it's 0, it means we look at it from the top. So how to get a function from this distance that gives us a value between 0 and 1? There are multiple ways of doing this, but I found what works for me is using the arctangent function. So let's have here scalar. Arctangent, given a value, is going to output a value between 0 and half pi, actually. So 1 point something. And to get it between 0 and 1, I'm going to divide here by half pi. Now this tells us how much we have to scale. And we can use it in combination with this direction vector here, but not the difference. So this difference here now incorporates also the distance in it, because it doesn't normalize. We need to normalize here to get this direction. So direction is normalizing this vector that we had there already. And now with this direction and the scalar, we can scale here differently. So what we do is we scale the direction, which is a vector between 0 and 1 in magnitude, with this height times the scalar. So the direction just gives us in which way to do the scaling, and this says by how much relative to the height. Let's save this, refresh, and now you can see it's a little bit funny what happens here with the trees. Focus on the trees, because the houses still work as before. And the reason why this happens is that the arctangent quite quickly goes up close to half pi. So we need to slow it down a little bit. And I'm going to go here and say divided by 300 is something that works, I think. Let's save and refresh. And now focus on the trees again. They look okay, but when we move like this, they don't become stupidly tall anymore. They are bound by that 200 height. And we can do the same thing for the houses as well. So everything we did for the trees, we're going to do for the houses as well. But this logic really belongs in some kind of function. Let's refactor this. I'm just going to delete everything and type it again. Maybe the logic becomes clearer if we do it again. And the function will be get fake 3D point from this center and this viewpoint with this height, like so. So let's add it to utils here at the end and re-implement the same logic pretty much. So get fake 3D point viewpoint height. And first step was to get the direction between the viewpoint and the point. We only want the direction, not the magnitude, so we normalize. And then the distance we need, because we will use it to figure out how much to scale between 0 and 1. So we use the arctangent from a shrunken value of this distance so that it spreads out more and we don't quickly end up at half pi. But because we have half pi, we have to divide by half pi to really get a scalar that is between 0 and 1. And now this scalar, we will return the point, adding at the point the direction scaled by this height combined with the scalar. So how much of the height in the direction it should move from the current point. That's how you get the top things. We save, and let's do the same thing for the buildings as well. In building.js, we go at the top, and instead of height coefficient, we just keep height. Let's also keep it at 200. I'm fine with this height. Height, height, and here we remove this and just use the function we created. So get fake 3D point, viewpoint, and this height, 60% of this height. That's how tall the walls are going to be. And we're going to copy this here, essentially in the same way, but we don't need this 60%. We just have 100% of the height. Save, refresh, and now the houses look more realistic when moving like that.